I welcome you all to another video tutorial session on finite element procedure for solving one-dimensional structural problem. In this video session, I'm going to solve a symmetric one-dimensional structural problem. I'm not going to solve this problem by hand calculation or using the finite element procedure by solving it on MATLAB as I always do in my previous video tutorial. I'm not going to solve it because this problem is very similar to to what I've done in my previous video tutorial. What I'm going to do in this video tutorial, I'm going to solve this problem on Ansys, and I'm going to show you how to use the symmetric functionality in MATLAB to solve this problem. To explain the problem that we're going to solve today, we see the full model figure A. We have it has three parts. The first part is 100 mm long, the second part is 300 mm long, and the third part is 100 mm long. We can see that about this center line of axis, the structural body is symmetric. For us to use the symmetric functionality in finite element procedure or on finite element software, we need to make sure that the structural body is symmetric, both in geometric, in material, and in loading property. This is what I mean when I say the structural body should be symmetric in geometric property. As like this body, what is on the left-hand side of this problem, the shape on the left-hand side is what's on the right-hand side. So we can say that this structural problem is geometrically symmetric. But for material, to explain the material symmetric, the material property on the left-hand side should also be equal to the material property on the right-hand side. Like this body, the whole body, as we're assuming, is made up of aluminium, 70 gigapascal, one structural material. So we can say we have aluminium on the left-hand side, we have aluminium on the right-hand side. So the body, this structural problem is symmetric. How I put it is symmetric by material. Assuming part 1 is aluminium and part 2 is steel, this body is no longer symmetric. We cannot use the symmetric tool in finite element software and to solve this problem by reducing it by half. Again, the last one, for us to define the body as symmetric by load, the loading on the left-hand side should be exactly what is on the right-hand side. Like in this problem, we have 15 kilonewton on the left-hand side pointing to the left. We should also have 15 kilonewton on the right-hand side pointing to the right. We have 10 kilonewton pointing to the left. We should also have 10 kilonewton pointing to the right. So this problem we have is symmetric by geometric, by material, and by loading. Therefore, we can use the symmetric functionality in the Ansys static structural solver to solve this problem. So it means that we can reduce this problem by half by taking a section, half of it, this part. And what it means actually is that along this center line of axis, we don't have there is no deformation along that center line of axis. the Q, or the Q, let's define our deformation quantity as Q. The Q is 0. So along the center line of axis, the body moves to the left or right under loading. That is what it means. So it means that we can actually apply a pin joint at the center of the structure, at the position of our line of symmetry. We can apply a, oh sorry, my sketch is bad. We can apply a pin joint at this point that prevent movement in the x direction. This body can move, this body, the response of this body to 15 and 10 kilonewton force is to extend the body to the right in tension. So when we mean symmetric, when we at that line of axis, there is a quantity, a deformation quantity that is always equivalent to 0. So for this equation, the deformation quantity along the x direction at this point is equals to 0. So it means that we can apply a pin joint at this position. So this is what we mean. In my first one-dimensional problem which I solved in my previous video, I actually placed a pin support at this end, and we solved this problem. So this is one way of solving this problem. This is another way of solving this problem. This is one way, this is another way. Either we place a pin support at this position, or we place a pin support at the midpoint, and we only consider half of the structural body. I will show you what I mean in my next slide. So there are two ways of solving this problem. Either we place a pin support at node 1, and we consider 15 kilonewton force at node 2, 15 kilonewton force at node 3, and 10 kilonewton force at node 4. Or we consider just half of the structural body by placing a pin support at the midpoint of our structural body, which is this. You can see from here to this point should be 150 mm. So I have 150 mm here. So I'm placing a pin support here, and I'm only considering half of the body. So now this is my first finite element for this finite element model. This is my first finite element. This is my second finite element. So we are going to solve this two problem on the Ansys program, and we are going to compare the results. So that is the objective of today's video tutorial. Actually, let me show you the results which I got on Ansys. But I'm going to explain how I did it in some minutes. So this is the full model. You can see the full model for element 1. We have 10, the area force in each part for element 1 is 10,000 Newton. You can see it's also 10,000 Newton in the half model. For the second part, it is 25,000 Newton. And we can also see that in the half model, it is 25,000 Newton. For the third part, it is 10,000 Newton. Also in the half model, it is also 10,000 Newton. So we see that the response of the body is the same for the full model and also for the half model. I actually did two full model here to illustrate a point. In Ansys, there is a symmetric tool which you can use to denote our support. So I use the symmetric tool for this half model here, and for this model at the middle, I inserted a pin support at this position, just to illustrate that either we use the symmetric tool in Ansys or we insert a pin support here, we get the same results. Also have the deformation plots. The deformation plot is actually different because for the full model, we are assuming our zero displacement at the beginning of finite element 1 at this point. But in the half model, we are assuming our zero displacement at this point. But to compare the full model and the half model result, we can compare the deformation at, say, this point at the end of finite element 3. It is 0.2768. This value should be twice the value in the full model analysis. So 2 times 0.2768 is equivalent to this value, 0.5336 mm. Also, this value here, 0.1 at this joint, that's the beginning of finite element 3. The deformation quantity is 0.13394. If we multiply this value by 2, we get this value, 0.41073. So it shows that the result is actually identical both for the area color plot and the deformation color plot. Let's move to the Ansys software where I will explain how we can solve this problem in the work environment. Now we're in the Ansys work environment. So the first thing we do, we activate our static structural solver. Drag and click the static structural solver to the middle of the screen. We need to define two materials in the engineering. We need to define one material in the engineering data because in our problem question, we have E1, E2, E1, and they are both 70 gigapascal. Well, our material is made up of aluminium, and the Young modulus of aluminium is 70 gigapascal. In the full model, it is just one material property. In the half model, it is also one material property, 70 gigapascal, 70 gigapascal. So we are going to define just one material in the engineering data. I'll name it aluminium. Then I will add the isotopic elasticity property to aluminium. Define my Young modulus for aluminium, 70 gigapascal. The Young portion ratio can be any value. I checked on the internet, typical value 0.34. I will close the engineering data. So I've defined my engineering material. Next thing, we move to the geometric workflow. Here we need to first activate the line bodies, and we double click on the geometric button here to open the space clean working environment. I think the space clean working environment is active now. I will open it. So I want to draw along the XY plane. So I'll make the XY plane active by clicking this button here, selecting the XY plane, bringing it to view. So we need to define what I intend to do. I'm drawing 3 structural body. I'll draw this full model, and I'll withdraw 2 of this half model in my space clean working environment. So I want to sketch the full model first. The material 1 is 100 mm. The length of material 1 is 100 mm. The length of material 2 is 300 mm. The length of material 3 is 100 mm. So I'm going to define this in the space clean working environment now. So click on the line body to sketch the line for each material. So from the 0, coordinates, I'll draw my line, 100 mm, 300 mm, 100 mm. and you zoom out, press escape on your keyboard to leave the line, to deactivate the line command, but the line command is still active. Now I want to draw the half model, which is given here in the problem question. The first finite element in the half model is 150 mm, that is half of 300. The second one is 100 mm. So I'm going to define that in my space clean working environment. I'm going to draw this line from above the full model, from the center point. Press Shift on your keyboard to reference dimension from this the center node point of finite element 2. Go up. So I want to sketch my line. Enter 0 as your x coordinate. Tab to move to a y coordinate. Enter say 150. So this defines the beginning of my node point, which I want, which is directly above the center point of our full model sketch. So the length of this first part is 150 mm. I have that. It's already defined as 150 mm. The length of the second part is 100 mm. I'm using the track node functionality of the space claim to get my dimension. The second part is 100 mm. So I've defined my first half model. I'll do the same thing. I'll do another half model directly above this at 150 mm from this node point. Press Shift on your keyboard and move the cursor to the upward to the right. Enter 0 as your x coordinates. Tab on your keyboard. Enter 150 to define the initial point of your line. So the first finite element is 150 mm. The second is 100 mm. So now we have defined our three structural body. We can end the sketch now. In our problem, we need to define the cross section of each line body. And in our problem question, we were told that A1 is 100 mm square, A2 is 400 mm square, and the A for this third part is also 100 mm square. So in my previous video, I've always been using rectangular section for my model, but in this video, I want to do something different. I'm using a circular section in my model. So I need to, for A1, I'll use a circular section. For A2, I'll use a circular section. For this A here too, I'll use a circular section of this area parameter. A1 will be a circular section of 100 mm square. A2 will be a circular section of 400 mm square. So let's go to the space clean working environment to specify our cross section. We go to the Prepare tab, Profile, click on circular section. So I've added a circular section, but I need two of it because we have 100 mm square and 400 mm square in our structural problem. So you click on the button, the circular button again. So now you will see, we check the beam profile, you see two circular sections. Now we need to edit the area parameter of both sections. Our first area section is 100 mm square, and we check under this deriving dimension, we have a parameter called R, and R is the radius of the circle, and it's defined as 10 mm. So we need to find the area of our first cross section, and we know that we need to find the radius of our first cross section, and we know that the area is 100 mm square. If the area is 100 mm square, we can calculate the radius as 100 divided by pi square root. So 5.64189 blah 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 is the radius of 100 mm square. So I'm going to paste this value in this position, copy paste. So I've defined my radius of my first cross section as 5.64 mm. I'll close this tab. I'll do the same thing to the second cross profile. Click on structure, beam profile, circle tool, right click, edit beam profile. Click on the radius parameter. The cross section area for our second area is 400 mm square. So it will be 400 divided by pi square root. So the radius of 400 mm square is 11.2837 mm. I'll copy it and I will paste it at this position. So now I've defined the cross section area of our both section. Now we apply each cross section to our line bodies. So we'll start from the 100 mm square circle, which is labeled circle. So we click on circle here, click on this button, create button, to apply the circle cross-sectional profile to our model. The 100 mm square in our question is applied to finite element 1 and finite element 3 of our full model, and also applied to finite element 2 of our half model. 100 mm square, 100 mm square, 100 mm square. So I'm going to apply this property to these line bodies now. So now click on the create button here and select this line, select this line, select this line, and select this line. The remaining is for the 400 mm square. So you have to change the cross section to circle 2, and then you select this line, select this line, and select this line. Now we have applied our cross profile to our line bodies. Press escape on your keyboard to leave this create function button. So if you go to the structural tree on the left hand side of your screen, click on this beam, you'll see the list of your structural elements which you just created. Here we have about 1, 2, 3, 4, 5, 6 structural body. So, and we need to actually change all of them to linked source type element. Currently, we see that each of them are defined as beam. So what you can do to apply the linked source type element to all of them, you can select all the beam, the structural beam, and under type, change to linked source type. So you see I've changed everything all together to a source element. So after you have done this, click on this button here, design 1, and change shared topology from none to share. So this is all we need to do on the space clean working environment to define the geometry of our model. So we can leave the space clean working environment by closing. Now I've left the space clean working environment. We go back to the workbench, and now you see under the geometry workflow is checked. That means our geometry model has been well defined. We go to the model workflow button and we double click it to open the mechanical work environment. It takes some time. The mechanical work environment is still coming up. Now the mechanical work environment is fully active. Let's check our geometry to see what is in our geometry. So we have all our parts under the geometric folder. Our material. So we need to specify the material property for each part. And we see this source element. This source element here, you can see this is highlighted blue, meaning that this is our circle 1. This is our they are all aluminum. So I'll just change the material is we only have one material property. So I'll apply the 70 gigapascal material property, Young modulus, to everything at the same time. Select all the source, the structural elements, all the source structural elements, and go to material assignment, change the material from structural steel to aluminum. So now we are done with material assignments. Everything, if you should check everything now, you can see they're all defined as aluminum. Now we can move to the mesh. Our greatest element size in this model is 300. So I normally define my element size for one-dimensional analysis as the greatest dimension in my finite element model. So I enter 300 mm. The element order, I'll use linear. I'm not using quadratic. So I'll define the mesh parameter. We go to the static structure. Here we need to define a lot of boundary condition. For our full model, we have one boundary condition at node 1, but because we need to reduce our problem to a one-dimensional problem, we also need to place boundary condition at node 3, at node 2, node 3, and node 4 of the full model to restrain the movement in the y direction, in the vertical direction. So I'm going to place 4 boundary conditions in this full model at node 1, node 2, node 3, and node 4 respectively. But at node 2, node 3, and node 4, the boundary condition will be just to restrain the y, just to restrain the y movement. At node 1, I will apply restraint in the x, y, and z direction. So under the static structure, click insert, right click insert, look for displacement supports, select the node 1 of the full model, apply the displacement supports to that node. I've applied. You can see we have one vertex under the geometric now. So I'm defining the x, y, and z as 0 at that node. So now I've defined the boundary condition at that node. I'll define boundary condition at node 2, node 3, and node 4 in the y direction also. So what I need to do, right click, insert, displacement support, select this node 2, apply. In the x direction, I want it can be movement. In the y direction, it can be movement. In the z direction, it can be movement, but in the y direction, I want to restrain movement. So what I can do, I can duplicate this displacement support. I will duplicate 2 of it, and I'll apply displacement 3 to the third node. And you see the y component is already set to 0. I'll do the same thing for displacement 4. I'll select the fourth node, and I'll apply the displacement support to the fourth node. The y component is already set to 0 too. I'm going to apply, now moving to the half model analysis, I'm going to apply zero displacement boundary condition in the x and y, in x, y, and z direction at this node. So what I can do, I can duplicate this displacement supports boundary condition here, because it has zero displacement in the x, y, and z direction, which is what I want. So I'll duplicate that. So I've duplicated the displacement boundary condition. This is it here, displacement 5. So I'm going to apply this displacement 5 to this node. I'll select this node, apply. We need to restrain movement in this node and also in this node, in the y direction. So I will duplicate, say, displacement 4. I will duplicate the boundary condition of displacement 4. I will apply this displacement 6 to this node. I'll do the same thing. I'll duplicate this displacement 6. I will apply displacement 7 to this node, restraining movement in the y direction. For this second half model, this is where we will apply the symmetry tool of Ansys. Here I'm using like a pin type of support. I restrain movement in the x, y, and z direction. I don't need to apply any boundary condition here. I just need, there is a tool called Symmetry in Ansys. So you go to this model button on the left hand side of the screen, you right click, insert, Symmetry. So when you click on it, you see a folder here called Symmetry. I click on the symmetric, insert, and click on symmetric region. So we need to define the geometry for the symmetric region. We will select the node where we want to apply this symmetric region tool to. So I want to apply it to this node in our half model here. So I've applied the symmetric region tool to this node. For at this node, and at this node, we need to restrain movement in the y direction too. So I'm going to duplicate this displacement 7 boundary condition. I'll make 2 of it. So 8, I will apply 8 to this node. 9, I will apply 9 to this node. So I've defined all our boundary conditions for the problem. Now we need to apply our load. And in the question, we're told that we have a 15 kilonewton load at node 2 pointing to the left, 15 kilonewton load pointing to the right at node 3, and 10 kilonewton load pointing to the right at node 4. So 15 minus 15 at node 2 plus 15 at node 3 and plus 10 at node 4 for the full model. I'm going to define these loads in the mechanical work environment now. So click on static structural, insert force. At node 2, we have minus 15 kilonewton. So I'll apply this load to it. I'll define the load by component in the x direction. Our axis, our degree of freedom is in for our member is in x direction. So the load is in x direction. So I'll enter minus 15 kilonewton, which is minus 15,000 newton, the x direction. I will duplicate this force, and I will apply force 2 to the third node, and I'll change the force to positive 15,000 newton. At node 3, I'm going to apply a 10 kilonewton force at that node, duplicate. I will select the node, I will apply force 3 to that node, and I'll change the load to 10,000 newton, positive 10,000 newton. So for our half model, we'll have 15 kilonewton load at this node. I'm finding it difficult to select the node. At this node, we have 15 kilonewton force, and at this node, we have 10 kilonewton force, as specified in the question. 15 kilonewton force at node 3, 10 kilonewton force at node 4. So I'm going to duplicate force 2. No, I'm going to duplicate force 2 because it's similar to the load I want to apply at this point. I'll duplicate it. So force 4 has been created. I will apply it to this node. Force 3, I want to apply it. I want to duplicate force 3 and apply it to this node. So I will duplicate force 3 and I will apply it to this node. Force 5 is currently defined as 10 kilonewton. I don't need to change it. Means I don't need to change it. I'll do the same thing for our last half model, the second half model. Force 4, I will duplicate force 4 and I will apply this force to this node. Duplicate force 5 and I will apply force 7 to this node, which is 10 kilonewton. So we have defined our load for the 3 finite element model. Now we can add our deformation color plots, our results, what we want to see, our deformation, want to see deformation color plots, want to see the area force color plot, want to prove the reaction. So you click on the solution, you click on the solution button, insert deformation, directional deformation in the x direction. We already set to x directions. Click on solution, insert beam result area force, solution, insert probe force reaction. I want to know the force at displacement displacement boundary condition. The displacement boundary condition is this boundary condition here. I want to know the reaction. I want to know the reaction at sorry. I will duplicate this, duplicate, and I will change displacement boundary condition to displacement 5. Yes, I want to apply. So I'll change the displacement boundary condition of force reaction to displacement 5. So I want to visualize this result. I will click on solve to run analysis. Let's see what Ansys gives us. So the result, the model is analyzing on the Ansys program now. Um, it has analyzed. Now let's check what the Ansys gave us as our result. Under the directional deformation, if we click on the Z, on this Z axis, we have this view. Zoom in. Let's play the deformation and let's see the result. You see, our full model and the half model, they are moving in the same direction. At the middle, but the deformation color plot is different for the full and half model, but they behave in the same manner. Let me end this animation. Let's probe the value at node point. So here we have 0. 0 in the full model, the 0 displacement is defined at node 1, but in the half model, the 0 displacement is defined at the center of the structural body. At this node, we have 0.14286. At this node, we have 0.13394. At this node, we have this value. At this node, we have this value. At this node, we have this value. We have this value here. We have this value here. So we see for our two half model, the values are the same. 0.2768 at this node, 0.2768 at this node. At this node, 0.13394, 0.13394, and 0 at the initial node for both half model. To compare the half model and the full model results, because the full model has two parts of this, it means that the deformation at this end, which is 0.5536, will be half the value of the half model. If we should divide 0.5536 by 2, we should get 0.2768. Let me show you on the calculator so you know that I'm not lying. 0.5536 divided by 2. So you see we get 0.2, exactly 0.2768. The same thing at this point, where we have 0.41073 mm. If we divide this value by 2, we get 0.13394 mm. So we see that the results are actually the same. The full model and the half model for the color plot are actually the same, but just that we're having half the results in our half model analysis for the deformation. If we should check the area force, we will see we have the same value of area force in our element. I should use the probe tool. You see the middle part of our full model, the area force is 25,000 Newton. If we check this, it's also 25,000 Newton. The response is the same. Here is also 25,000 Newton. Here it is 10,000 Newton. Here is 10,000 Newton. Here is 10,000 Newton. Here is also 10,000 Newton. The first reaction here will be we check the tabular. It should be this 10,000 minus 10,000 Newton. While the first reaction at this is minus 25,000 Newton. It's like the algebraic sum of the forces in that direction. That's just it. There's nothing unique about this value actually. So this is how we analyze symmetric problem on the Ansys program. I would like to show you one more functionality of the Ansys program before I end this video tutorial. We can actually mirror the color plot result of our half model. We can mirror the results so that we can visualize full results on the Ansys program. I will show you how to do this. So let me close this table here. For us to mirror the results, I would like to hide this full full model analysis. I don't want it displayed because once I apply the mirror tool, it's going to also mirror the full model color plot, which I don't want. I only want the half model color plot to be modeled. So I'm going to hide the full model. I'll do this by under the geometry. I'll select the full model structural elements. That's three components. I'm going to suppress it. Okay, instead of suppressing, let me see if I can hide body. I think I can hide it. I'm not going to suppress it. I'm just going to hide it. Okay, I'm not suppressing it. I hid the body. So to use the mirror tool, what we need to do, we need to actually activate a tool in the workbench, the Ansys workbench. First, we need to close this mechanical work environment. And under the workbench, work environment, under the tool option, we need to make sure under this appearance tab, we need to make sure this beta option is checked. So make sure this beta option is checked and click OK. Now go back to the mechanical work environment by double clicking on this model tab. And then we will now use our mirror tool of Ansys. The mirror tool is a beta, it's actually a trial tool. It's under development. So that's why we needed to do this to make sure it is active. So what we need to do now, under the model, click on the model, right click, insert symmetry, not symmetry. Okay, symmetry is already inserted. Okay, go to the symmetry folder. Under the symmetry folder, you will see graphical expansion 1, graphical expansion 2, graphical expansion 3. Because we want to mirror in one direction, we're only using graphical expansion 1. If we want to mirror in, if we have a two line of symmetry, we use graphical expansion 1 and graphical expansion 2. But because we only have one line of symmetry, we're only using the first part, the graphical expansion 1. So the number of repeats, we want the number of repeats to be set to 2. And we need to do something. We need to create a new coordinate. I need to create a new coordinate where I will define this point here as my 0, 0 coordinates. We need to do that. It's very important. This node here, I need to define it as my 0, 0 coordinate. So under the coordinate system, I click on it, insert new coordinate system. So because I selected that node and I created the new coordinate system, the new coordinate system was automatically inserted at this point. And when you insert your new coordinate system at that point, you should make sure the x-axis of the coordinate system points in the direction of your model. As you can see, my x-axis is in the direction of my structural element. So go back to the symmetric folder, number of repeats 2, type, we have Cartesian polar 2D symmetry. We want to choose Cartesian. The full model, we want to choose half model, but I want to show you what the full model will do. If you define this as full model, this is what you have. That means you have to, this delta S, you have to, the length of the full length of our half model is this is 150 mm long, this is 100 mm long. The full length is 250. That means you have to divide this as 250 mm. And this is what you have when you check results. True results are it displays a copy of A copy of the half model is displaced 250 mm from the 0, 0 coordinate, which is this part here. This part here. But what we need to do, we need to use this the method. We need to use this half. The method we need to set it to half instead of full. So this is what actually mirrors our half model in the other direction, setting this method to half. And what we need to do, we need to set this delta S to a very, very small value. If we should set it to 0, it will not work. So you type a very, very small value as your delta S. This value has to be negative because you want to mirror it in the other direction. So minus 0.0001. So check the results. Ooh. I'm not getting what I'm supposed to get. What happened? Oh, I think I understand what happened. Sorry. I didn't change the coordinate system. The coordinate system is defined as my global coordinate system. The new coordinate, you need to change this coordinate system to your new coordinate system, which is the coordinate system that is attached to this node. To this node there. So if we are to check the result now, we see the half model has been mirrored in the other direction. Let's view it in the x direction. So if we should play an animation, we'll see our structural body behaving the way we want it. Under the load, both sides, the structural body is in tension, stretching in both directions. So this is how we display the full result of half model of a one-dimensional structural problem on the Ansys program. So this marks the end of a one-dimensional problem using finite element procedure. In my next video, I'm going to move to finite element procedure for solving source structure. We're going to solve plane source problem. We're going to solve 3D planes, 3D source problem, three-dimensional source problem. We're going to solve. We're going to consider a symmetric truss, and we'll model a symmetric truss by half using the symmetric functionality of Ansys. Also, we're going to analyze a truss system with inclined roller support. So those are the problems we're going to tackle using finite element procedure in my subsequent video tutorial. I think let me show you the problem, our first problem, which I'm going to solve in my next video tutorial. We are going to solve this particular problem. MATLAB application to plane truss system. So this is a cantilever type of truss. It is supported at its edge by pin support. It is 4 meters long, 2 meters deep, 1 meter deep. So we are going to apply finite element procedure to solve this problem in my next video. Thank you so much for taking the time to watch my video. I'm so grateful. Stay tuned and look forward for my next video tutorial. Thank you so much.